Cloudflare. We got asked yesterday, what are we doing here? Well, we got invited, but we're here to talk about some work that we did last year on improving ARM security chain, primarily for server-grade CPUs. So a lot of us are used to ARM in the embedded systems or smaller microcontrollers. Well, we'll get into why we need it. So I'm Derek. I've been at Cloudflare for about 3 years. I work as a staff engineer, and I'm joined by Ryan and a quarter of his girlfriend's face. So I did promise I wouldn't make Ryan this headshot. But he's been here for a couple of years, and we focus, we're more involved on the defensive side. So a lot of the talk's been involved in the defensive side, but we're more focused on the defensive side because of the scale of our network. And we work on securing Cloudflare's infrastructure, primarily on the research side. How can we get better security out of our hardware? So a little overview. We're just going to talk about who we are for those that are not really familiar about what we do, not necessarily from what everybody knows, but kind of like what we work on internally. And our original security journey, it kind of gives us a little bit of context to some of the decisions that we made when we were going down this path. How we implemented our original hardware root of trust, the background on ARM secure boot, what we did and what we researched, and kind of some of the things we found that were missing. This new concept called single domain secure boot, and then Ryan's going to finish up with a demo, some talks about what's left to do and some of our future work. So Cloudflare, we're known for stopping DDoS attacks, and we stopped pretty massive ones. But we're also a web performance and other types of security company. In order to maintain kind of the level of defenses that we do for defending some of these attacks, some of them were 2 terabits a second that we stopped, we have to maintain this capacity. And so we maintain a very, very large network. This is kind of from our public stats, so it keeps kind of our marketing team happy when they see it, because everybody likes to know what we do. But this kind of shows the vastness of our network. To the point where these numbers constantly change and we kind of forget where we are. So we find out that there's a new data center somewhere, and we have to make sure that everything's kind of consistent with our security framework. 270 plus cities. We have interconnects with over 10,500 different networks in the world. 142 terabits of network capacity. A lot of internet properties. People know us from our DNS resolver, so 1.1.1. We're consistently handling over 16.1 million DNS queries per second. So we designed Cloudflare's network to be able to handle every single service on every single server, and that's what kind of comprises our edge, and it allows us to be able to kind of distribute things ad hoc and at whim. But this is a hardware security conference, so lots of cities mean lots of servers. We have to constantly keep up these stats. And we don't take things that are off the shelf. We don't put things, what we have in our systems, we don't buy from, Dell, as a Dell branded server. They're highly customized, they're highly bespoke, and we use multiple original device manufacturers or ODMs in order to be able to kind of have a lot more control of how we manufacture our equipment and also take advantage of additional global warehousing, especially in our supply chain crisis. So, our developers and our customers don't really worry about how their services are protected or the underlying architecture, but we do. Because we are located globally, we have to worry about from the initial build and have initial manufacturer to how it's shipped, source port, destinations, VAT offices, customs. It can't multiple hands actually touch our hardware before it actually ever gets powered on. And so that became kind of part of our threat model, and we had to figure out how do we implement better ways of being able to protect our hardware and hardware. So this is our first iteration of secure boot. It's very, very basic. It's just a little bit different. We started with having our trust anchor with our UFI firmware, spines platform key, trusted database. We don't use the default ones that usually come with servers that are Microsoft keys. We actually do something a little bit different. We create platform key that's used to sign updates and trusted database that contains a signed list of option ROMs, PCI hashes, similar to what you expect from secure boot. And then these variables effectively make up our master key that's used to sign all these other resources, IPXC, chain load scripts, kernel drivers, so forth. But we realized when we anchored here, obviously there's other problems that exist. So we've learned a lot about UEFI vulnerabilities over the last few years, seen by the classes here. There's more methods that are coming nowadays to circumvent a lot of protections to maintain persistence on our systems. And it taught us, that when you anchor you have your trust anchor within your BIOS firmware, it only protects the bootloader. It doesn't protect the firmware itself. And so, when we look at things like, weak protections or configuration, those are things that usually we fix through like automation. So what we really were interested in is things that maintain persistence, these little bit plans. And so, LoJack, Mosaic Aggressor, and most recently Moonbounce taught us that, regular secure boot checks for modification of the bootloader, and checks for the PCI option ROMs that sit outside of system firmware. But, if these checks are being implemented in firmware, then the firmware would just be checking itself. And so we presented this, kind of this information internally, and somebody said, well, why don't you just use TPMs? TPMs are great. They have, but they don't detect against TFI implants. Alteration of UEFI firmware is persistent and invisible. TPMs are used for static root trust measurements. They're actually implemented within UEFI firmware to initialize the TPM to start this process of hashing root code into PCRs. And so PCRs would show whether or not the root process has changed. But if your UEFI firmware has been compromised, then it just wants to follow those measurements. So this scared us. Our hardware goes through many steps, and so knowing this, we had to look at ways of being able to mitigate this. So back in late 2020, we talked about how we started using AMD EPYC processors in the Generation 10 hardware. Thinking that the SoC is this AMD secure processor that allowed us to be able to extend our PKI trust boundary into hardware. And so this is AMD's version of hardware secure boot. And so platform secure boot verifies the first block of boot code before releasing the CPU from reset. So it's verified through a set of hashes stored within this customer bank of GPU uses within the SoC. This talk isn't about AMD specifically. Again, it was just mainly to kind of like set context for some decisions we were making later. But I wanted to show the decision flow for kind of like image authentication as we use it to reference, the upcoming slides. With some other things that are kind of optional, based off of whether or not you want to enable things like secure debug or anti-rollback features. But the idea is that you have this, trust chain of keys, some that are AMD rooted public keys within the SoC that vary per SKU, and then, customer issued public keys. And then it goes through this decision process of determining whether fuses have been blown. If fuse is blown, validate the contents. If it's not, then authenticate and validate it. And then it goes through determining things like model ID, version, and whatnot. And then it checks these root of trust measurement signatures. The firmware was the first block of boot code signed. It updates the register values. And so ideally you're looking at for either, hey, it passed, everything was cool, it does a x86 release from CPU reset, or not. If any of these conditions fails to boot. So awesome. So we updated our secure boot chain. We now have everything rooted in hardware, allows us to be able to validate our firmware. But again, this is enough talk about x86, so let's talk about ARM. So ARM secure boot. For those that know a little bit about it, there is something that's kind of equivalent to this. And we started looking into ARM processors for our next generation hardware for a lot of the power efficiencies that come with it. A little bit of background, ARM Trusted Boot Board Requirements, TBBR, or also known as ATF Secure Boot, was originally architected for cell phones. It was the precedent set by LG, HTC, Samsung, and Qualcomm, and gave us a reference example on how to build this concept of a chain of trust within the ARM community between the first ROM executed in bootloader 1 to the handoff to normal world, from secure world to bootloader 3.3. The soft manufacturer is heavily involved with secure boot chain, required a unique SKU per customer. For one customer, probably would be bad, but most manufacturers have thousands. The stock manufacturer was responsible for the end-to-end signing and maintenance of the PKI chain. It's a big one. It's complicated infrastructure. I talked to some of my peers, some of these companies that have implemented this this, and they said, we require multiple internal signing authorities, USB key fob, and so forth, and it really doesn't scale. Scales well in the cell phone community, scales well for small and architectures, but we're looking at servers, high-grade servers. So what was meant for kind of like, cell phones really wasn't meant for servers. So if we were involved 100% in the manufacturing process, this wouldn't be much of an issue, but we're customer and consumer. So one thing we do control is how our servers are designed, our block diagrams, and so forth. So we looked at ways of being able to kind of like learn what we did from the AMD side, implement them, within the ARM world, and looked at kind of like design partners. So start looking at Ampere, specifically their Ultramax single socket rack server CPU provides great performance, really high power efficiency per core, and that's what we're looking at from a reduced power consumption standpoint. Only a small set of subset specs from here, but Ampere backboarded various features in the Ultramax, specifically speculative attack mitigations that built that Spectre. They pulled them from the ARM v8 5 instruction set architecture, hence why there's this designation of ARM v8 2+ extensions. So the diagram here, again, if you're familiar with ARM TDR, then some of these components are going to actually be, fairly, they're going to be understood, but I'll explain them anyways. It shows the ARM processor boot sequence implemented by Ampere. So at power on reset, the system control processor, which is comprised of two processors. So it's split up in something called system management, which handles obviously system management, everything but frequency and thermals, and then this power management, Pro, which obviously handles frequency and thermals. So it runs the system management bootloader from ROM and then loads this SM Pro firmware, and this spawns the power management stack on the PM Pro processor, and also launches the ARM trusted firmware threads. The ATF bootloader 2 and bootloader 3.1 bring up resources such as DRAM and PCIe, and then after this, control is passed over into this normal world, which is your bootloader 3.3 BIOS, and then use grub and whatever to grow us. So the standard authentication flow, and including like the storage ICs as well, at power on, SM Pro firmware reads Ampere's public key, which is stored in this that's CPU-ROM. From this key certificate from the ROM and computes a hash and compares this with Ampere's public key. Hash is stored in eFuse. So once authenticated, Ampere's public key is used to decrypt and content certificates for SM Pro and Pro ATF firmware, which are launched or described above. So the SM Pro public key is used to authenticate SM Pro and Pro images, as well as ATF keys, and in turn will authenticate ATF images. And so this is kind of like this cascading set of authentication that forms this eFuse root of trust domain. So this is the original root of trust domain that Ampere used for signing system secure world firmware. It's the normal world over here. So when we looked at this and we started referencing the signing process we had within AMD, and we knew there was a large enough bank of OTP fuses, we just thought, well, why can't we insert our key hash here? That's what we did. So single domain secure boot, or this concept, is take the same authentication flow and adds a customer key hash to the eFuse domain, making this like a single root of trust, or single domain secure. This enables verification of UEFI firmware by hardware root of trust, processes performed already validated ATF firmware from bootloader 2. So we, the customer, our public key and DB variable format is read from UEFI, secure variable storage, and a hash is computed and compared with the public key hash through eFuse. So if they match, the validated public key is used to decrypt the PL through content certificate validating and launching BIOS, and then eventually the related guidance. So this is kind of like the key feature of single domain secure boot. It validates the entire boot chain with a single eFuse root of trust on the process. So this is this provision. And so kind of like, as like what the basic of the details of what single domain secure boot is, just adding customer key hash in there. What we we have to know is that when our servers get built, all UEFI firmware gets signed. And so we include kind of like the provisioning manufacturing process because it's kind of like a little background detail about people. So break it down a step. So this is very inclusive. There's 3 parties involved. Usually it's your silicon manufacturer, an ODM, and then a customer. So in our case, us, and we all play a role in this execution phase. So first, we, the customer, we generate certificates for a public-private key pair using our internal secure PKI. The public key side is provided to our ODM as DBB auth and DBU auth in secure variable format. So Ampere provides a software reference package, SRP, that includes your BMC, SCP, UEFI, and CPLD firmware to the ODM, and they customize it for our platform. So the ODM will generate a board file describing the hardware configuration and also any customizations to the UEFI firmware, which allows us to be able to enroll those secure variables within storage and at first boot. So once it's done, we generate a UEFI slim file using our ODM's UEFI ROM image, ATF, and board file. So this is different from what we encountered with AMD Platform Secure Boot insofar as that the entire image and ATF files are signed, whereas with AMD PSB, only the first block of boot code is signed. So the entire slim file is signed with our private key, producing a signature hash in this file, can be only authenticated by the correct public key. And then finally, the ODM packages this UEFI into an HPM format compatible with their platform BMC. So in parallel, we're providing debug fuse selection and regarding the OTP fuses that we're going to use, as well as a DIR formatted public key. A hash of our DIR formatted public key. So Ampere uses this information to create a special version of their SCP firmware called security provisioning or SecProv. And this firmware is only run one time. It's to program the debug fuse settings and our public key hash into the socket fuses. So normally they use this security provisioning when they are implementing their hash values within the storage ICs. So since we're inserting our hash into this root of trust domain, it's run for us as well. So Ampere will deliver this SecProv sim file to our ODM, and then they convert it into a compatible file format for whatever BMC firmware update tooling we're using, Sock Flash, Yahoo Flash, or whatever. So during system manufacturing, the firmware is pre-programmed in storage ICs before placement on the motherboard. Note that the SCP firmware is not using your standard SCP firmware, but the SecProv image. And so after the system is powered on, an IPMI command is sent to the BMC, which releases the Ampere processor from reset, and this allows the SecProv firmware to run, burning the socket fuse with our public key hash and debug fuse settings. So manufacturing flow. Once our public key has been provisioned, manufacturing proceeds by reprogramming SCP PROM with its regular firmware. Once the system powers on, ATF detects that there are no keys present in secure variable storage and allows the UEFI firmware to boot regardless of signature. Since this is the first UEFI boot, it programs our public key into secure variable storage and reboots. ATF is validated by Ampere's public key hash as usual, and since our public key is now present in DBB format, it's validated against the public key hash in eFuse and allows UEFI to boot. So validation. Don't worry, we're almost there. So the first part of validation requires observation of successful destruction of the eFuses upon automatic or manual issue of an IPMI command, OEM command to the BMC. The BMC observes a signal in the SecProv firmware denoting eFuse programming completion. This can be probed through a BMC console. So when the fuses have been blown, validation continues by observing the boot chain of other firmware. So any corruption of SCP, ATF, or UEFI firmware obstructs the boot flow and boot authentication and will cause the machine to fail booting. So once other firmware in place, this happy path validation begins with so upon first boot, you have firmware boots in the following order: BMC, SCP, ATF, UEFI. And so the BMC, SCP, and ATF firmware can be observed via their respective serial consoles. So UEFI will automatically enroll the two DBB files, DBB and DBU auth files to the secure variable storage and trigger a reset of the system. After observing this reset, the machine should successfully boot to the OS if the feature is executed securely. So for further validation, we can use a UEFI shell environment to extract the DBB file and compare the hash against the hash submitted to Ampere. After successfully validating the keys, we can flash an unsigned UEFI image, which Ryan will show in a bit. And an unsigned UEFI image will cause authentication failure at bootloader stage 3.2. So the ATF firmware undergoes a boot loop as a result, and similar behavior will cause for a UEFI image signed with incorrect keys to not boot. So back to this UEFI authentication. So in revisiting this flow and all subsequent boot cycles, the ATF will read the secure variable DBB, our public key, compute a hash of the key, and compare it to the read-only customer public key hash in the eFuse. If computed and the eFuse's match, our public key variable can be trusted, and it's used to authenticate the signed UEFI image. And after that, the system will just boot to the OS. And so that's kind of how we completed it. So I'll hand it off to Ryan for a quick demo of how it works.
Yeah, sure. So we were unable to get a machine without a single domain secure boot enabled. Supply chain issues. Really easy thing is late this weekend. But all we have here is I'm going to flash some unsigned firmware, go back and forth between the signed firmware. There. So there's our signed BIOS. We're in user space there. Going to go ahead and try to flash my malicious unsigned firmware. You can imagine someone trying to flash whatever they want, be able to disable and enable settings that we don't want enabled and disabled, namely even UEFI secure boot, performance settings, etc. I'm going to speed through this really quick. Awesome. I'm just going to reboot the machine here. Cool. So at this point, we really don't see much, naturally. We might get a UEFI secure boot violation, but underneath, there's still things going on. As Derek had mentioned earlier, the SCP still boots. It's still trying to read out that Ampere private key and compare that initial hash and check that public key hash. From there, it goes on to the ARM-trusted firmware world. And there, it'll attempt to try to load the DBB, try to calculate our customer public key hash and compare it against the OTP fuses that were burned in via some IPMI command. I'm just reflashing the signed BIOS here. But at this point, this is where the failure occurs, mainly because there's no public key hash to be calculated since the DBB and DBU are not present. Awesome. Reset the machine via remote interface, and we'll boot back into and observe the BIOS screens. Awesome. Exhilarating, I know.
It boots.
It boots.
It boots.
Awesome. So that means our entire boot chain is secure, right? Well, not quite. As we've seen earlier, the BMC is actually the first boot device. And for those of you who don't know what BMC is, it's baseboard management controller. It's really this device that really allows lazy sysadmins who don't want to visit the data center to turn off and turn on the machine, get some system event logs, get some sensor information, etc. So why attack it? Well, highly privileged access to the host. These devices were not designed for security. They were designed for functionality and ease of use. Not only do they have highly privileged access to the host, they have access to the low pin count bus and the South Bridge. And for those of you who don't know, that basically allows access to PCIe devices, storage, RAM, power supplies, fans, etc., and a whole plethora of sensitive things if someone were to try to attack us physically, or worse, try to access some data. It's network accessible. another large attack vector. And with this device not being designed for security, it's extremely vulnerable. IPMI is still a very commonly used protocol, the Intelligent Platform Management Interface. But it's not quite so intelligent. It was developed in the 90s, and majority of servers still use it today. And being network accessible, has access to the management and host network, and it just has a poor firmware security history. Again, the sensitivity of how close it is to those sensitive peripherals within a server chassis just make it a really prime target for attacking. So what can we do about it? Well, we can, sign our BMC firmware and check in firmware, but it doesn't really do anything if we can just wipe our firmware and flash it with something else. We can implement features similar to single domain secure boot within some BMC platforms, but we also run into the same issues that we run into with single domain secure boot and AMD's platform secure boot, where it makes things difficult to e-cycle. Supply chain, we would like to help reuse these machines later and pass it on, but that would mean us giving up our private key in order for someone else to flash their own UFI image or BMC image. And also, it's just another standard operating procedure for us to manage. AMD has their own for their secure boot, ARM has their own, and now we have to manage all these different device-specific operating procedures. But the last thing that we're interested in trying is some CPU agnostic infrastructure to enable a cryptographically secure host prior to boot time. Some of the vendors shown here are some of the organizations that are focused on trying to create that unified platform secure boot architecture. Moving away from the platform-specific stuff, we get to use puff-based identity keys to components, not just for the BMC and the UEFI, but also those peripherals within the chassis as well, because we don't have to use OTP fusing. And then we have this concept of key transition. Now that we no longer have to burn immutable hardware to compare our signatures against, we're able to manage our keys more effectively, rotate, revoke things if necessary, provision new keys if necessary as well. Thanks for listening to us. Come check us out at blog.cloudflare.com. And thank you very much.
Do we have questions? 1, 2, 3. No questions. Okay.
So it looks like in the future you're planning on that new piece of hardware for key management, but currently does that mean if your private key were somehow compromised that basically all of the hardware that you have signed with that key is kaput? You have to basically burn it down and start again?
Yeah. I mean, ideally, I think these, AMD started something that was really good because it allowed us to be able to kind of move it or implement this hardware root of trust in something that was actually very, very simple process to do. The problem is that we're dealing with many different CPUs. And then we also have to deal with different CPU generations. So there is a root key rotation per SKU. So a next generation CPU from the same vendor is still going to have a separate key, which is great. It's a good thing. It's kind of implementing proper key rotation. But yeah, if your private keys compromised, you have other problems. So again, it's probably really good internal PKI practices. The only reason we're looking at kind of going down the security coprocessor route is because it allows us to maintain consistency. We build a lot of different types of devices, and so if we're able to size it based off of the device, then we have kind of a consistent SOP on how to implement a good root of trust across all of our devices.
Thank you.
Oh.
Any other questions? Okay, if there are no questions, thank you,
Awesome.
Derek and Ryan.
Thank you.